Okay. So thanks, Yue, for the introduction. And it's my honor today to sort of come here and give a presentation on sort of my understanding for the warehouse multi-agent planning and also the sort of a little bit vision here on sort of how to use RL. Um, so to start, let me maybe just one slide to kind of explain why we want to consider RL for this problem. I think one kind of my personal inspiration is that in the past year we do observe a lot of successful RL applications, starting from AlphaGo. But most recent examples may include like in the case of like DeepSeek, people use RHF, GRPO for train reasoning model or kind of in the sort of AI agent system now becomes very hot. People start to explore how to kind of using RL to train AI agents. And actually, in this year, the Turing Award was awarded for two kind of founding fathers for RL. So I think that's a sign, sort of, RL is everywhere, and we do want to kind of explore how to use it for different applications. From my personal experience, I also kind of did a bunch of applying RL to different fields. One particular field is actually for supply chain, sort of optimizing the order fulfillment. Um, so quite related to the warehouse problem. That's why sort of I started to get interested in this problem. Actually, my background is in operations research, and I'm an assistant professor at Columbia University, Columbia Business School. So I didn't really have much experience kind of in terms of thinking of multi-agent path finding. But I had a friend, Jiaoyang from CMU, and she introduced me to this problem. I started to get interesting and thinking about, where RL here can help. And actually, I get very interested in this problem. I think uh, in terms of like why learning can kind of help here comparing to sort of traditional optimization or search-based method. My intuition is mainly twofold. One is that the learning can somehow kind of introduce this new perspective of learning from the environment, because in the real environment, kind of in warehouse, the demand is always changing, and you want to sort of quickly adapt to the new sort of a demand pattern, and that's the one thing you can learn from the environment. And two is that you can also learn from the historical kind of instances, which when we do optimization, we somehow sort of overlook that perspective. So I think that's kind of the promise brought by the learning and the reinforcement learning kind of framework. But there are also a lot of challenges as I kind of learn from this competition. Um, so I think so far, from the previous teams, we have talked a lot about the details of this competition. For now, I want to take a small detour here from sort of a related problem where I have fortunately observed the success of RL in the real world systems. And this related problem is called ride sharing. And the ride sharing kind of a famous example is for like Uber and Lyft. And those are the company they kind of they operate. Their success is based on the success of how good they are solving the ride sharing, ride hailing problems. And in particular, for that system to work, you will see it is actually very similar to sort of the warehouse problem. So in their problems, the problem is like, when a user comes to the system, when you kind of open your Uber, you sort of you have a request, right? And so the request is that you want to go from your location to a destination, and then in the system there are many drivers, like sort of in the system. Some of them are available, some of them are not. And the system has to, decide which driver to sort of pick you up. So there is a matching problem they have to do. Also, like you can also call it a scheduling problem. And then once you kind of have decide, which driver to come to pick you up, and then you need to do a sort of a routing problem. To make the problem even more complex, they also have a pricing layer that is very important to Lyft and Uber. they can also decide actually the reposition of the car sometimes to sort of like if the sort of driver is available right now, the driver can actually still move to sort of to the location that has expected like higher demand. So it's arguably it's actually a more complex problem than a warehouse environment because in the warehouse you have many things that is under your control, but here many things are not out of your control. But even under such a scenario, I think in the past maybe 2 to 3 years, we actually have observed the sort of success of deploying RL in such systems, and that's actually my sort of motivation of like, hey, you're like, can we borrow something from the ride sharing? Can we kind of try that in the warehouse system and see how it goes? Um, this is actually one kind of table from the Lyft kind of paper talking about sort of how good, what are the benefits of RL in their system, and we can actually see it improves sort of the it improves the ratings and helps the matching system, and overall it actually increased by $30 million per year in terms of revenue. So it's making I think a reasonable like big impact there. Um, I kind of want to sort of walk you through a little bit, in the Lyft system, like how exactly they are using RL, what are the main sort of insight in such a system. And actually, interesting enough, the insight is quite related to the sort of the first talk we have today from from Professor Amanda, in terms of how would you think about the graph neural network to optimize sort of RL function, value function. So to just make the problem like as simple as possible, the main sort of the framework they are solving in terms of ride sharing or this kind of scheduling and the routing problem, I think the main thing here is the scheduling. Because in the ride sharing system, the routing is usually not that challenging. The congestion problem is not that crazy. So in terms of scheduling, in the end, you are trying to solve sort of a matching problem, right? In terms of each driver can only match one kind of rider, and for each matched edge, you will have a cost or sort of a weight. That's called the Wij. And in sort of the ride sharing system, usually people, every few seconds they are trying to solve a matching problem. Every few seconds solving another matching problem. Sometimes they use Hungarian, and most of the hack in the past have been kind of focused on sort of how to heuristically design the Wij. And I kind of observed the same thing here, because essentially when we design the scheduling algorithm in this competition, we are somehow playing with Wij. As we see from the maybe it's Versterand team, I think you are kind of designing all kind of congestion function, which is speaks to Wij, right? And so the same thing happened also at Lyft. And then I think in the end of the day, they're kind of trying to say, like yes, we can kind of handcraft all the Wij, but can we have a learning-based method, inspired by IL to learn those Wij automatically? So the answer is actually they actually find a way of doing this, and the perspective is the following: if you consider the whole system together as a large RL problem, your states are from each driver is an end state system, and your goal is to learn a kind of a policy pi that map the system to sort of your action, which is which driver you want to match, and then you collect the reward, and then you transit to the next system. But the challenge here is that if you want to learn such a system using RL, like inevitably your state space will be exponentially large. The value function you have, let's say for Q value, which is a long-term reward, is going to be exponentially large. So very, very challenging to learn. And the hack actually used by Lyft is the following. Essentially is decomposing the Q function into the sum of a local Q function, where each local Q function is defined not on all the drivers, but on single driver and single location. And by doing this, essentially they are kind of using this heuristic of the value function to sort of enable them to learn this Q value much easier than before, because now you can learn it with each single location or each single driver. And by doing this now, after you learn the value function, you can essentially replace your sort of a Wij. Previously, you defined it by some heuristics. Now you can use this RL learned value to sort of a guide the design of this Wij. And now to estimate a local value function, there are many methods. And one method you can do kind of in the lift system, for example, is using the TD learning. And interesting enough, so this is kind of the framework used in kind of left. And I think one lesson we are learning here is that actually, instead of a handcraft designed weights, potentially we can use RL-based method, and we can use some decomposition kind of heuristics to learn those values and to help us to guide the design and guide the optimization. And here is actually a map learned by the lift to show you sort of the values of different location. Essentially, it's kind of telling the sort of a driver where are the locations you want to go. So that actually matched the kind of intuition in terms of the traffic in the city. Um, Another interesting point is that people don't have a really good understanding for what kind of system you can decompose in this way. And recently, we actually have a new discovery, which is to sort of fundamental understanding for this kind of decomposition, and also connects it to sort of the quantum entanglement. In terms of what we find is that if the system, the Markovian system, is entangled in a way similar to quantum entanglement, then it's hard to decompose. Otherwise, it's easy to decompose. In some sense, there is a theory now to guide you how would you decompose a value function like this. Um, so why I'm saying this is a preliminary, very preliminary kind of exploration, because there are still a lot of challenges applying this framework to our competition, and we were trying, but we only get a very preliminary like results. And because in essence, what we find is that there is implementation wise is not easy. Training is also very costly. RL is data hungry. And also, I think in our competition, there is a big issue about the congestion. And our method is not that well designed for the congestion problem. As you can imagine, in the lift system, there is not that much congestion. So there are some challenges here, but we do see kind of improvement in a few instances, sort of brought by RL. Um, but we don't. So in terms of the solution we submitted, we are trying, but in the end we don't sort of we didn't get time to make RL method work pretty well. So the solution we submitted actually are very similar to the No Man's Sky, the sort of the first team. The solution actually very similar. We are using sort of the window parallel PIBD plus LNS, the sort of best solution from previous year for pathfinding. And for the scheduling part, we are using something very similar to the No Man's Sky solution, which is a global greedy algorithm with some a little bit heuristic. Um, and that's the solution we submitted, but then we kind of explore more in terms of the RL. And personally, I still believe there are a lot of potential for sort of RL method, a learning-based method, to sort of shine. And I think that is, but it requires more exploration. And I'm also welcoming more kind of people join together to sort of do this exploration together. That concludes my talk. Thanks, everyone.
Thank you for the talk. We have time for one question. Is there a question from the audience? So I have one quick question. So in the last slide, you're showing the result for sortation from the I approach, right? So
This one?
yeah. So
Hmm.
is a baseline refers to the approach you submit to the competition, or is
Uh,
it baseline from what?
yeah, the baseline referred to the one we submit to the competition. So which is strong baseline.
Okay, so it's like R perform better in these two maps.
Right. But
Okay.
still, I think it's very preliminary, so I will take it for a kind of a grain of thought, just some evidence for the kind of the future potential improvements.
Yeah. Okay.